probability of E1 is a person met with an accident. The probabilities of all E1, E2, E3 are non-zero probability. That means they must be greater than 0. So probability of getting head when a coin is tossed is 1 by 2. Probability of choosing a bag which contains both as a gold coins is equal to 2 by 3. Hello everyone, a warm welcome to one and all. This is your Shruti ma'am, Vidhyaashram School of Excellence, Mysuru. In this session, we are going to study about the concept Bayes theorem. So before that, let us see what is partition of a sample space. Suppose we consider E1, E2, E3 as the partition of a sample space. Then let me consider a sample space here. So it is divided into 3 events, E1, E2, A3. So clearly, if you consider E1 intersection E2 or E2 intersection E3 or E1 intersection E3, so they are pairwise disjoint. And if you take the union of all these three, that is E1 union E2 union E3, so this is equal to the sample space, and the probabilities of all E1, E2, E3 are non-zero probability. That means they must be greater than 0. So the events E1, E2, E3 are said to be the events under the partition of a sample space if they are pairwise disjoint. That is, if they are mutually exclusive and exhaustive events. Exhaustive means the union of all the events should be equal to the sample space and their value of the probability should be always greater than 0. Now here, a set of events is said to be represents a partition of a sample space if they are mutually exclusive and exhaustive events and have non-zero probabilities. Let E1, E2 until AN be a partition of the sample space S, then EI intersection EJ. Here I and J may represent any event. So they must be pairwise disjoint. That means all the events must be mutually exclusive events. And the union of all the events must be equal to the sample space and the probability of an AV event should be greater than or equal to 0 for all I from 1 to N. Theorem on total probability. Let E1, E2, En be a partition of the sample spaces and suppose that each of the events E1, E2, En has non-zero probability of occurrence, then A be any event associated with the sample space S. Then probability of A is given by probability of E1, probability of A given E1 plus probability of E2, probability of A given E2 plus probability of E1, probability of A given E1. So this is the concept of conditional probability along with the sum. Hence this theorem is called as theorem on total probability. Now suppose let us consider E1 and E2. So they are the events in the partition of a sample space. Then clearly we can understand that E1 union E2 is equal to S and also E1 intersection E2 will be equal to empty because they represents the partition of a sample space. Let A be any event in the sample space. Then A can be written as A intersection S. We know that S can be written as E1 union E2. So using the concept of distributive property, we can write this as A intersection E1 union A intersection E2. Now if we apply the concept of probability here, then probability of A is equal to probability of A intersection E1 plus probability of A intersection E2. So this can be written as using the multiplication theorem of probability, probability of E1, probability of A given E1 is already happened. Then probability of E2, probability of A given E2 is already happened. So if E1 and E2 represents the partition of the sample space, then for any event A, the probability of A can be given as the sum of this, that is probability of A intersection E1 plus probability of A intersection E2. Similarly, this concept can also be extended if we have three events like E3, then the same thing is repeated here, probability of E3 probability of A given E3. So if we extend until the concept of n number of events in the partition of a sample space, then the last one will be probability of A intersection En, and hence here it extends until the last event, probability of En, probability of A given En is already happened. Hence the total probability of any event in the sample space is given by summation I varies from 1 to n, probability of EI, probability of A given EI. So this is nothing but the total theorem on probability. So the same thing is represented in this form here. So instead of I, here I have taken J. So therefore probability of any events A with the partitions E1 to En can be represented as summation of I varies from 1 to n, probability of Ej, P of A given Ej is already happened, where J varies from 1 to n. So since this is the summation, it is simplified in this form. Next one is the Bayes theorem. So what does the Bayes theorem states here? If E1 and E2, En are mutually exclusive and exhaustive events associated with the sample space, and A is any event of non-zero probability, then probability of EI given A is already happened is given as probability of EI, probability of A given EI divided by the total sum. So let me consider this now. Probability of EI over A can be written as probability of EI intersection A divided by probability of A using the conditional probability. So probability of an event where another event is already happened is equal to the probability of simultaneous occurrence divided by the probability of the other event. So here EI intersection A can be written as probability of EI dot probability of A over EI. So using multiplication theorem of probability, and we know that probability of an event A with the partition of a sample space is given by the total probability. So therefore here this can be replaced by this. Probability of Ej, probability of A given Ej is already happened. J varies from 1 to n. So this is the Bayes theorem. So which is derived from the conditional as well as the multiplication theorem on probability. Now let us take the problems related to Bayes theorem. First problem, bag 1 contains 3 red and 4 black balls, while bag 2 contains 5 red and 6 black balls. One ball is drawn random from one of the bags and it is found to be red. Find the probability that it was drawn from bag 2. So now let us take the probability of choosing bag. Let probability of choosing bag 1 be E1 and probability of choosing bag 2 be E2. So we have only 2 bags. We need to select any one bag. So obviously the probability value is 1 by 2. Now let A denote the event of drawing a red ball from any one of the bag. So drawing red. Now, what is the probability of getting red ball from bag 1? So we know that in bag 1 there are 3 red and 4 black. So in total, out of 7 balls, we have 3 red balls. So therefore it is 3 by 7. And what is the probability of drawing red ball from bag 2? So we know that in bag 2 we have 5 red and 6 black balls. So out of 11 we have 5 red balls. So it has to be 5 by 11. My question is, I need to calculate the probability of choosing bag 2, that is bag 2 where a red ball is already drawn. So using Bayes theorem here, probability of E2 given A is already happened. So using Bayes theorem to calculate probability of E2 given A is already happened can be written as probability of E2 given A is equal to probability of A intersection E2 divided by probability of A. Again using the concept of multiplication theorem of probability, we can write this as probability of E2, probability of A over E2 whole divided by, this can be written as the sum of total probabilities, that is probability of E1, probability of A, conditional E1 plus probability of E2, probability of A, conditional E2. Now we know the values, individual values of all this. E2 and E1 is 1 by 2. Probability of A over E2 is 5 by 11. A over E1 is 3 by 7. So therefore here 1 by 2 into 5 by 11 whole divided by 1 by 2 into 3 by 7 plus 1 by 2 into 5 by 11. We can remove 1 by 2 in both numerator and denominator. So numerator 5 by 11 whole divided by, so we are left with 3 by 7 and 5 by 11. So we have 11 3s are 33 plus 7 5s are 35 whole divided by 11 7s are 77. So here we can cancel 11 1s are 11 7s are 7 5s are 35 whole divided by 68. So this is the value of the given probability. Next question. Box 1 contains 2 gold coins while another box 2 contains 1 gold and 1 silver coin. A person chooses a box at random and takes out a coin. If the coin is gold, what is the probability that the other coin in the box is also gold? That means we need to choose box 1. So probability of choosing box 1 and probability of choosing box 2 is same, that is 1 by 2. Let A be an event of choosing gold. Then probability of choosing gold from bag 1 is equal to 2 out of 2 because there is only 2 gold coins here. So choosing gold coins, it will be same. Next, probability of choosing gold coin from bag 2 is equal to 1 out of 2 coins because there is only 1 gold coin out of 2 coins. Now I have to choose the probability of the other coin in the box is also gold. That means I need to choose the second coin so that it has to be gold. So that means I need to choose bag 1. So I have to find the probability of bag 1 where another coin is gold. So using Bayes' theorem, this is again probability of A intersection E1 divided by probability of A. So this can be written again in the form of probability of E1, probability of A, even E1 is already happened, divided by the total probability P of E1, P of A, conditional E1 plus P of E2, probability of A, conditional E2. So now substituting all the values here. So A over E1 is 1 and this is 1 by 2. So that is equal to 1 by 2 into 1 whole divided by 1 by 2 into 1 plus 1 by 2 into 1 by 2. We can remove 1 by 2 here, then we are left with 1. 1 plus 1 by 2 is 3 by 2. So the value will be equal to 2 by 3. So probability of choosing a bag which contains both as a gold coins is equal to 2 by 3. Next, a bag contains 4 red and 4 black balls. Another bag 2 contains 2 red and 6 black balls. One of the 2 bags is selected at random and a ball drawn from the bag which is found to be red. Find the probability that the ball drawn is from the first bag. So clearly I'll directly write probability of choosing bag 1 as well as probability of choosing bag 2 is equal to 1 by 2. Now if I denote A as an event where the ball is red, then probability of choosing red ball from bag 1 is 4 out of 8 balls and probability of choosing red ball from bag 2 will be equal to 2 out of 8 balls. So that is 2 plus 6, 8. Now I have to calculate probability of choosing bag 1 where red is found. So this can be written as again probability of A intersection E1 divided by total probability of A. Again, using the concept of multiplication theorem and total probability, we can write this as probability of E1, probability of A conditional E1 whole divided by the total probability P of E1, P of A given E1 plus P of E2, P of A given E2. So therefore, this will be equal to 1 by 2 into 4 by 8 whole divided by 1 by 2 into 4 by 8 plus 1 by 2 into 2 by 8. So clearly we have here 4 by 8 divided by 4 by 8 plus 2 by 8 will be equal to 6 by 8. We can remove half in both numerator and denominator. 8 get cancels. 2s are 3s are. Hence the value is equal to 2 by 3. Next question. An insurance company insured 2,000 scooter drivers, 4,000 car drivers and 6,000 truck drivers. The probabilities of an accident are 0.01, 0.03 and 0.15 respectively. One of the insured person met with an accident. What is the probability that he is a scooter driver? Now, probability of selecting a scooter driver is 2,000 out of 12,000 driver. So therefore it is 2,000 divided by 12,000, which will be equal to 1 by 6. Probability of E2, where the person is a car driver, is 4,000 divided by 12,000. So that is equal to 1 by 3. Probability of choosing car driver is 6,000 divided by 12,000. So that is equal to 1 by 2. So now here, if I represent A as the probability of accidents, then probability of a person met with an accident who is a scooter driver, value is given, that is 0.01. Similarly, we have P of A conditional E2 as 0.03 and probability of A with E3 is given as 0.15. Now my question is, I need to find out the probability that he is a scooter driver. That means probability of E1 who is a person met with an accident. So again this can be written as probability of A intersection E1 divided by the total probability, which can be written in the form P of E1, P of A conditional E1 whole divided by the total probability P of E1, P of A given E1 plus P of E2, P of A given E2 plus P of E3, P of A given E3. Now substituting all the values here, so we have the values as 1 by 6 into 0.01 whole divided by 1 by 6 into 0.01 plus 1 by 3 into 0.03 plus 1 by 2 into 0.15. So simplifying this, we'll get the value as 1 divided by 52. Next question. A man is known to speak truth 4 out of 5 times. He tossed a coin and reports that it is head. Find the probability that it is actually head. So let me consider the event E1 as the probability of getting head. So probability of getting head when a coin is tossed is 1 by 2. So probability of not getting head, which means getting a tail, is also 1 by 2. Now let A denotes the event that man speaks truth. Now the probability so that man reports that it is a head, that means he is actually saying a truth. They have given as 4 by 5. Then obviously he say lies. That means he says that it is actually head when it is not actually head, will be equal to the complement of this 1 minus 4 by 5. That is equal to 1 by 5. Now we need to calculate the probability that it is actually head. That is probability of E1 conditional A. So by using Bayes theorem, can directly write this as probability of E1, probability of A conditional E1 whole divided by the total probability P of E1, P of A given E1 plus P of E2, P of A given E2. Now substituting all the values here, we have 1 by 2 into 4 by 5 whole divided by 1 by 2 into 4 by 5 plus 1 by 2 into 1 by 5. So removing 1 by 2 from both numerator and denominator, so we are left with 4 by 5 whole divided by 5 by 5. So the value is equal to 4 by 5. Next question. A man is known to speak 3 out of 4 times. He throws a dice and reports that it is a 6. Find the probability that it is actually 6. Now let us consider event E1 as getting 6. So probability of getting 6 when a die is thrown is 1 by 6. And probability of an event where we will not get 6, it may be 1, 2, 3, 4, 5 in the dice. So we have 5 chances here. So it is 5 out of 6. Again, let A denotes that man speaks truth. That means he reports that 6 occurred. So the probability that man speaks truth when it is actually 6, that is, they have given 3 out of 4 times. So obviously the complement of that will be equal to 1 minus 3 by 4, which is 1 by 4. Now we need to calculate the probability that it is actually 6, that is, that the man has spoken the truth. What is the probability of it is actually 6 when man has already spoken the truth? So using Bayes theorem, we can write P of E1, P of A given E1 whole divided by the total probability P of E1, P of A given E1 plus P of E2, P of A given E2. So now substituting the values here, so we have 1 by 6 into 3 by 4 whole divided by 1 by 6 into 3 by 4 plus 5 by 6 into 1 by 4. Now we can remove 1 by 6 here. Then we are left with 3 by 4, 3 by 4 plus 5 by 4. So 3 by 4 whole divided by 8 by 4. 4 get cancels. The value is equal to 3 by 8. So this is the application of Bayes theorem in terms of these statement problems. So this is all about the chapter probability. I'll meet you in the next session. Until then, keep watching, keep learning, keep exploring. Thank you.